All right, welcome guys. This is Professor Eric Roldan here going over section 2.1 in Explorations in Math. So first of all, set concepts is what we're going to be studying this whole chapter. And just want to point out quickly that the founder of this set theory, which is basically about organizing and classifying information, is a guy by the name of George Cantor. So George, he's a Russian mathematician born in the 1800s, and so he is one of the pioneers in this area that we're about to study. Okay, so, well, what is an element or a member of a set? Well, an element is basically, it's a collection of objects in a set. Okay, so for example, we have so like the sets of cities in Polk County. Okay, where Southeastern is located. Well, Lakeland will be an element of that set, or a member of that set. Okay. Now, a well-defined set would be, basically, we use defined sets for descriptions. And I'll mention, so what we're talking about right now are descriptions of sets. We're using words and phrases and sometimes a whole sentence. So well-defined set is basically a set that can be clearly determined. So this is basically based on facts, not opinion, okay? Based on facts, not opinion. So for example, we have some facts that we can get, let's say from Southeastern, would be the sets of math professors at SCU. We could look that up. These are facts. We can go on the website and look that up. But what would be a not well-defined would be, let's say, the best math professors. Because everybody's going to have a different opinion about that. Okay, so this is based on opinion, so that would not be well defined. Okay, so let's see here. So now we have, let's say, we're going to go switch from descriptions to roster form. So basically, roster form is to be able to write the set inside braces, okay? And braces are basically these symbols here. Okay, those are not parentheses, okay, or brackets. If you see those symbols, that would not be considered a set. Okay, so it's not parentheses or brackets. So an example of that would be, I don't know, let's say the seasons of the earth. That's a description. That's well defined. Okay. So that would look like this. You got the braces, spring, summer, fall, winter. Okay. Another example, let's say natural numbers. Natural numbers are numbers that are counting numbers. They count. You can count them on your fingers. They don't include zero or any negatives. So we'll say capital N for natural numbers. Braces, let's say 1, 2, 3. And actually we can keep going forever. So we're going to use something called an ellipse. So basically that's like a dot, dot, dot type thing. Okay. Okay, other examples of sets besides saying the description or using roster form, like a list, would be set builder notation. Now this is something that's more used in algebra. So set builder notation sort of looks like this. And so this would be called, let's say, set D is the set of all elements X let's see here. Just a second. Okay, so the set D is the set of all elements X such that bar means such that. Let me do that again. Just a bar. And then the next part are the conditions for membership. Okay. Conditions for membership. So our example would be, let's see here. So an example that we could use would be, let's say, set E Okay, so this reads set E is the set of all elements X such that X is a natural number, is a member of the natural numbers, and is greater than 10. Okay, so just a quick word on this symbol means elements of. Okay, so X is an element of n natural numbers, 1, 2, 3, 4, etc., and is greater than 10. Okay, so that would be in roster form, that would be like 11, 12, 13, anything greater than 10. Okay, 11, 12, 13. So they're natural numbers. We're not going to include any decimals or fractions, and it's greater than 10. So that would include anything beyond the number 10. Okay, now let's do the cardinal number of a set. So let's say cardinal number is basically the number of elements in a set. Okay. The number of elements in a set is something you're just going to count. And it's symbolized by the letter N. In parentheses, let's say set A, for example. Okay, so let's say set A is 1, 2, 3, 4. Then the number of elements in this set there's 4 numbers in there, so that would be 4. Okay. Let's say set B. Let's say set B was set B was spring, summer, fall, winter, and it'll be the same thing. We count them 1, 2, 3, 4. That means the number of elements in set B would also be 4. Okay. Now, let's talk about equal sets. So equal and equivalent sets. So equal sets would be sets that contain exactly the same elements, okay? Uh-oh. Let me go back. Raise this up some. So equal sets are sets that contain exactly the same elements. Okay. So in this example, let's say set C is 1, 2, 3, and D is 3, 2, 1. Well, it looks different, but they have the same elements, 1, 2, 3. Okay, C and D. So we would say that our conclusion then would be that C equals D. Okay, they have the same exact elements, so they are equal sets. Equivalent sets would be a little bit different. And equivalent sets will be sets. Sets that contain the same number of elements. Okay. So for example, these two up here, 1, 2, 3. Whoops, 1, 2, 3, 4. B, which will be spring, summer, fall, winter. Okay, they have totally different elements, but they have the same number of them. They both have 4. So we would say that these are equivalent sets. Okay. So A and B are equivalents. But C and D that we looked at previously would be both. So this is equivalent only, and this are both equal because they both have the same elements, 1, 2, 3, and they're also equivalent because they both have 3 elements, same number of elements. Okay. Null or empty set. The set that contains no elements. Okay, none. So that would look like this. Okay, this is called empty. And a circle with a line through it is called null. Okay. For example, the set of months that begin with Z. What month is that? Well, there are no months in our calendar that begin with Z, so the set would be empty. Okay. All right, down to our last 2 words here for 2.1, and separate all these. So a universal set. Universal set would basically be the set that contains all elements in a problem. So for example, if we were if I said, hey, let's count, let's pick a number from 1 to 100. So I just defined the set from being 1 to 100. So our universal set, which we would show as U would be, let's say 1, 2, 3, 98, 99, 100. So it's 1 through 100 is the universal set. Okay, we could talk about everything in between those, including 1 and 100, but not outside of that. Okay, so that's the universal set, and we'll talk more about that in upcoming assignments. So now, something we kind of mentioned already is infinite and finite sets. Okay, so infinite sets you've seen. So let's say, like we had the set of natural numbers is infinite because it keeps going forever. There's no end. Another example would be the integer set. Integers now include a 0 and negative, so oops. So that goes forever to the left. 0, 1, 2, 3. Okay, and forever to the right. That's also an infinite set. A finite set would be basically the opposite, something that does stop, does have an ending, or something you can, the elements you could basically count. Okay, so we've talked about that already. Like we talked about set A being 1, 2, 3, or even the empty set. Okay, is finite. All right. So basically, that does it for all of our foundational definitions for chapter 2. We'll get into a few more as we go along every section, but now I'm going to spend some time doing some exercises from the textbook. Okay, starting on page 44. Okay, now that we're done with this, with the definitions, let's look at some exercises and put some of these words into practice or apply them. So we're going to start with, like I said, page 44, and we're going to do, the first couple we're going to do is 12 and 14. So determine whether each set is well defined or not well defined. And the first one is the sets of the most interesting movies in 2015. Okay, so most interesting is it a subjective or opinionated set? So that is not well defined. Okay. So the way to change that to a well-defined would be like the set of movies that won an award in 2015, and we could look that up. Those are based on facts. And we're not doing 13, we're doing 14. Okay, so number 14, the sets of Academy Awards winners in 2014. That's based on fact, so that's well defined. Okay, that can be looked up on the internet. It's not based on opinion. Okay, next set. Let's see. 18. 18 says determine whether each is finite or infinite. So 18 is the set of multiples of 3 between 0 and 40. And this definitely has a beginning and an end, so this is definitely finite. And feel free to stop the video if you want, try to answer it, and then press play to see what the answer is. Number 21 is next, and we're going to say the sets of odd numbers greater than 15. Well, that will be starting with 17 and going forever to the right, so that will be infinite. Okay. Next, 24. express each set in roster form. Okay. So the sets of months whose names begin with the letter J. Okay. So, oops. So January, February, March, April, May, June, July, August, September, October, November, December, and that will be it. Okay. Next would be 29. 29. Set of football players. Over the age of 70. So that we would have to look that up. But it says who are still playing in the NFL, which I would safely assume that none of them are playing, so we would have to say this set is empty. Okay. Okay, now let's go to number 42, which is on page 46. And 42 says express each set in set builder notation. So we have set A is 1, 2, 3, 4, 5, 6, 7, 9. There's a couple ways to answer this. So set A we can say is the set of all x such that x is, we can say is actually x is an element of the natural numbers, because those are not including the in-between numbers like 1.5 and 1.5 and all that. So does not include the natural number. It includes the natural numbers, a part of the natural number set, and x is less than 10. Or you can put x is less than or equal to 9. Okay? Either one of those would work. Next we have number 44. Take a look at that one, and that one is set D is equal to 5, 10, 15, 20. Okay. So we can say that we can do a description like x is multiples of 5. Or we can write the symbols for that, and we can say x is part of the natural numbers, and 5x. So if x is, the first natural number is 1, 5 times 1 is 5. And then the next natural number will be 2, so 5 times 2 would be 10, so on and so forth. Okay, so either one of these would work. Okay. Okay, so we also have, let's say 51. 51 is write a description of each set. So we have A, E, I, O, U. And that is basically going to be the set of vowels in the English alphabet. Okay, and 51 and 54. 54. X is an element of the natural numbers. Oops. And 4. Oops. 4. Okay. So we take it to look at the roster format. This is basically 4, 5, 6, 7, 8, 9, and 10. So a description of that would be set of natural numbers we can say between 3 and 11. Another way to say that would be the set of natural numbers between 4 and 10, and then use the word inclusive, and that's going to include 4 and 10. Okay, almost done. Just got a few more here, and we're going to go to 66 and 71. 66 says state whether each statement is true or false. So B is an element of the sets A, B, C, D, E, and F. So B is part of this element right there. So yes, this is true. B is an element of the set. Okay, you don't have to write all that, but just wanted to clarify. So 71 is 9 is an element of 1, 3, 5, 7, ... So those look like natural numbers that are odd. And so 9 would be a part of that. So this also would be true if you finish the pattern. So this is also true. Okay. So if you see this symbol, this just means not an element of. Okay, like 69. Three is not an element of, let's see, natural numbers, and X is odd. And that is false because it is a part of that. So this will be false. Okay. Two more, 78 and 82. Let's erase all this craziness. 78 and 82. So we have two sets, purple, green, and yellow. Okay, and we also have B, which is Q, R, and S. And the question is determine whether the pairs of sets are equal, equivalent, both, or neither. Okay, well, they're definitely not equal. They don't have the same elements, but they definitely both have 3 elements. Okay, so in other words, the number of elements in A is just 1, 2, 3. And the number of elements in B is also 1, 2, 3. So therefore, these are equivalent. They're not equal, but they're equivalent. Okay? Now, what about 82? Whoops. A is description form. A is the set of states. I'm assuming that's US. Okay, the 50 states. And then B is the set of capitals or state capitals. Okay. So states and state capitals, they would not be exactly equal because they don't exactly match. Although some states do have capitals with same name of the state, but those are going to be assumed to be all different. And we have, these are also equivalent. Okay. All right. So sometimes, like we said, sets can be equal and equivalent, or they could be neither. Okay. Now, we're going to go ahead and go to the second video, which would be 2.2.